Hi and welcome back to another series of analyzing the GitHub data with Firebolt. Today we will cover the queries that we executed in our previous application and also take a look of how those have been optimized using aggregated indices so that they return as fast as possible. So let's get started. So the app I wrote in order to query the data is based on StreamLit, which allows you to come up with small data apps really fast and create proof of concepts. And we will take a look at this. StreamLit is written in Python, so today we're gonna take a look at the Python SDK for Firebolt, but there's also other SDKs in other languages like Go or Java. So let's get started with the application. The first thing we should probably take a look at is the pip file, which lists the different dependencies. So we have StreamLit here, the Firebolt SDK, using a little bit of pandas and humanized to display dates in a more human-readable format. The second thing we're going to take a look at is the Firebolt connection. This is basically just setting up a Firebolt connection, reading from the environment, which engine and which database we would like to query, and then we have the username and the password. This sets up a connection and simply returns a connection. We're going to reuse this method across several files in our code base. So just a quick reminder before we take a look at the source, how the homepage looks like. And we see here that we're basically running a few queries based on the input at the top, right? This is the slider with the start and the end date. And that one is a filter that will be used for the total events, the total repositories, the total users, and also for the events and the events per type. So keep in mind that we have to make use of this filter. So looking at the source, we do see that there's a method called load GitHub Archive data. And it basically tries to extract the date filter and figure out when the start and the stop date is. And this timestamp filter over here is basically applied to every query. So we have a select count star, which is the total number of events. We have a select count on the distinct repository name, which is the total number of repositories being acted on. And we do have the same for the actor login. So those three queries basically resemble our three numbers at the top. The queries for the two graphs, for the two area charts, look a little different. So this one is basically grouped by either month or day, depending on the time range you select. For the full 8 years that we are displaying now, we pretty much end up with 8 years times 12 months, so about 100 buckets. And for the last query, we simply select for event type and count, and again, filter on the timestamp. And this is pretty much it. Those are the 5 SQL queries which are executed for this site. Then, if we take a look at how this is structured from a perspective of StreamLit, we basically have our title over here. We have the slider, we have the start and the end date, which is just written out one more time, the total duration. And then we already have the 3 columns here with the start and duration. And then over here, we have the other 3 columns with the events, repositories, and users being displayed. And for the area chart and the bar chart, we basically use a Python data frame, a pandas data frame, and show the time at the count and the type at the count for this. And that's about it. So the whole setup, the whole querying is just taking a couple of lines of Python. But what is probably more interesting over here is taking a look at the queries and why they are so fast. So let's head over to the SQL workspace in our Firebolt database. So here we are within our Firebolt database, and the table I used is called GH Archive. You can see here again, it has like the 5 billion rows, has a size of a terabyte, also has an uncompressed size, so we have a compression ratio of 5.6. But the interesting part, of course, is that I copied all the queries over. So those are the ones from the application. And again, I used the same date filter for everyone. And once we run those, we see that they're coming back pretty quick. But the interesting part is, if you keep in mind that we queried the database set in the terabyte size, that the bytes that needed to be scanned are much lower. And that's a common trick in databases, right? If you have the right data structures, where you can just query less data, your queries will become much faster. So one of the tricks is providing summaries. And this is exactly how this works, because if we take a look at all of the queries, they have some similarities. All of them use aggregates. We have count star, count distinct repo name, count distinct actor login, count star, and count star. And this is also the where clause is the same. So again, part of the queries are very similar. And the trick here is that we can basically do something within Firebolt that is about setting up a so-called aggregating index. In order to understand, we have to take a look how or what a query looks like. So let's take a look at the explain data of one of those queries. So we have an output here, and at the bottom we see that it's not actually the table GitHub Archive being queried, but it is an aggregated index being queried named main page count date filter. This is how I called it at the beginning. So depending which query you pick, there's another aggregated index being worked on because they're sort of optimized on the aggregation you're calling in combination with the where query or the parts of the select query. But let's take a look at one of those indices. So we do have all three of them. And if you remember, ours was called main page count date filter. So let's take a look at the index definition. And the index definition says that we're truncating on the day on the created at timestamp. And then we have basically the extracting the year and the month. This is because the data is partitioned on a monthly base. So this data structure exists for every month. And then we have the summary functions here, like count star, count distinct repo name, and count distinct actor login. And for these tuples, we sort of keep the counts for all three of them. So instead of having to do a real count when a query hits, we can just exit this data structure and return the count as soon as possible and as fast as possible, because it just has become a simple lookup instead of an expensive computation. And this is one of the tricks why those select queries are as fast as they are. Thanks for listening, and see you next time, where we'll take a closer look of how this dataset is actually indexed. See you!